Okay, good morning everyone. Today we'll move to some equations are necessary to allow us to estimate the concentration, which is important to further estimate how many available carriers, especially here we will focus on the concentration for the electron holes. And in today's, we focus on the semiconductor in equilibrium. So which means this is the case that we consider that there's no external force that apply to our semiconductor material. It's purely to consider that the case under the equilibrium. And for sure later we will also discuss the case under the non-equilibrium, which is the case that we start to give a certain bias or under the different temperature, and then therefore there will be the change in the carriers. So last week we have already discussed the most important part is that how do we understand, how do we apply the quantum series for the solids, especially we start to discuss about the Venn diagram, how this Venn diagram concept coming from, and then why we will use this Venn diagram to understand how actually the electrons and then the carrier transport. And then also in last week we already discussed, in the case of semiconductor, we are not only interested as a small amount of carrier. Actually, we are interested in the whole behavior of a large amount of carriers. So we will introduce certain statistics rules that allow us to estimate the whole behavior of the huge group of the carriers. So based on what we have been discussed last week, we will move on to further consider how to start to estimate the concentration in the semiconductor. So that's the purpose for today's lecture. So the first one is that we are very curious about the charge carriers in semiconductor. And as we already described in the last week, that there's a very important statistic, that's what we call as a Fermi-Dirac distribution. So in the case of Fermi-Dirac distribution, the formula that we have discussed last week, which is shown in here. So we have the number of carriers over the number of the quantum state is equal to our probability here. And so the top one, this is a number of the electrons. For example, in the case, it's number of the carriers. And the bottom one is number of the quantum states. So this is the equation that we have already considered in the last week. So now we will, everything from today's lecture will based on the Fermi-Dirac distribution. So first of all, we will be interested to understand the equilibrium distribution of electron and holes, which can be estimated from the equation as shown here. So the number of electrons, number of the carriers are equal to this times this. So therefore, is equal to GCE times FFE. So this is equation coming from the Fermi-Dirac distribution. And the next stage is that we consider as a thermal equilibrium electron concentration. Therefore, we can estimate the thermal equilibrium case. So the N0 here suggests this is under the case of the thermal equilibrium is equal to integration of the GCE times FFE with a different energy level. So now we are trying to estimate the thermal equilibrium concentration, electron concentration with the integration of this function with a different energy level. So for electrons in the conduction band, so we can consider our energy is larger than EC. And if EC minus EF is much larger than our thermal energy, then also this will be larger than this one. So in this case, as we already mentioned last week, this is a Fermi-Dirac distribution, which can be approximately by consider the Boltzmann approximation, and therefore this equation becomes minus EF over KT. So this is a Boltzmann approximation that we also have already mentioned in the last week. And also, the GC is estimate here. That's also something that we mentioned last week, that we don't spend the time for this equation calculation, but this is just to show that the GC is estimate from here. So now we actually just try to put everything here. We have a FE here. We have the GC here. So ideally, we can start to estimate the thermal equilibrium electron concentration. So based on these two equations with the integration, then in the end we can have this one, which is shown me here. This is a full equation in detail with GC. This is a GC times our FFE. So this is our starting point. So far, I think this is just a very simple mathematic tricks that we put what we have already learned everything together. But now we just do some very simple approximation. Therefore, we use the Boltzmann approximation, and then we start to put the equation and try to integrate, and then try to understand that what would be the full picture for this thermal equilibrium electron concentration. For sure, to further understand this equation, we still need to do some more clever way to visualize this equation. So actually we can also consider use a simple graph with band diagram with GC to understand this thermal equilibrium electron concentration. So we already know that this is a typical band diagram where we have the EC and EV. So this is our band gap with the top as a conduction band and then bottom as a valence band. And also from the last week, we already mentioned the GC can be have the characteristic similar to this one. This is our GC. And this is our GV. So if you forget it, you can check the slide from last week. And now we can try to also plot the Fermi-Dirac function here, where first of all we have the Fermi energy here. So you have to try to turn in a different direction to understand the Fermi-Dirac distribution. But now, because last week what we mentioned, what we try to plot is the x-axis is the energy level, but now we turn to the y-axis as the energy level, and therefore our distribution function, which is will be look like in this way. So this will be our distribution function. And this point is our FFE here. So now with the help from this graph, which this is our GC, and this is our distribution function. So with the help from this plotting can give us more sense that actually how we start to estimate the thermal equilibrium concentration. So therefore, the equation that we try to estimate here, which is GCE times FFE will be equal to the NE. This is our equation that with a different energy level. And this one is imply that we are actually trying to estimate these two curves. This one times this one. And therefore, the conclusion is actually we are trying to estimate the area here. So try to be more obvious. So actually, the integration of this function with this function, actually what we try to estimate is the area in below, because we try to times these two curves together. And therefore, this equation suggests that we are trying to estimate the area here. And this area is as equal to thermal equilibrium electron concentration. So like I said before, that although if you try to look at each individual equation, probably it's difficult to understand. As we say, last week we already mentioned this equation. If you purely try to look at this curve, definitely it's difficult for you. And last week, we also start to describe this distribution function. If you try to only look at this distribution function, for sure, it's difficult to understand what would be the application. But now, if we look at this equation, so the concentration is actually just this one times this one, and that is equal to this curve times this curve, which actually suggests that our area in here is equal to our electron concentration. So in this sense, actually it's pretty easy to be understand. And similarly, if we try to calculate the GV E times 1 minus FFE here, that would be equal to the PE, which is a whole concentration. So this calculation also suggests that we try to estimate the area here, which the area is equal to P0, which is a whole concentration. So that's actually this equation try to the information from this equation try to deliver, which is suggests that with help from this distribution function times either GC or GV, in the end suggests that our concentration is equal to the area here, which can be the electron concentration or the whole concentration. And of course, for understanding, I think it's always easier than the equation calculate. But for sure, we still need to derive some more equation to get the analytical way to estimate our electron and hole concentration. So we will, based on the concept and the idea here, we will continue to do some more sophisticated equation calculate here. So in this case, for sure, we will still try to do our best to solve this equation. This is the equation that we already shown in here. And then with a certain consideration, for example, we can put as a E minus EC over KT as a eta. And then we can also put this number as a constant 1, which will be equal to, we define this one as a NC. Because of, if you look at these equations, it's just a constant. It's just matter with our material property and temperature. So we can consider this is a constant. So we define this as a NC, which we call as a effective density state functions in the conduction band. And therefore, we consider this as a fixed constant number, then therefore in the end we can have this equation, which is pretty well known in our semiconductor. This is the equation we use to estimate the thermal equilibrium electron concentration. And for sure, for your homework and the exam, you will need to use this equation very often, because this can give us a very efficient way to estimate our electron concentration. And from this equation, actually there are several suggestions. The most important is that our electron concentration here, N0, is dependent on EC minus EF. So that means if now we consider the case EC minus EF decrease. So what does EC minus EF decrease? The EC minus EF decrease, that means from the concept of a band diagram, we have EC, we have EC and EV. And the EC minus EF decrease, that suggests that our EF is actually getting close our EF is getting close to our EC, right? So that's why the EC minus EF decrease, and EC because the EC and EV are the fixed line that we cannot change. That's mainly dependent on our band gap for our semiconductor material. The only things can be possibly adjust, which is EF. So the EC minus EF decrease suggests that actually the EF is close to the EC. But also, on the other hand, if you look at this equation, the EC minus EF becomes smaller, suggests that our exponential of this term, EC minus EF over KT, the exponential of this term is increasing. Right? Because of, I think this is a pretty simple mathematics, so that this one decrease, and this is exponential minus of this term, for sure that once this decrease, the overall term is increased. So that suggests our N0 is increased. So now, in the case of the N0 is increased, so that means in terms of this semiconductor material, we might have our electron concentration is larger than P, larger than hole concentration, larger than P0. And this also suggests that this is becoming as an N-type semiconductor. So this conclusion is very important. You don't have to remember the equation all the time. From this equation, probably once you pass these courses, you won't need to understand or remember this equation anymore. But at least the physics suggestion coming from this equation is important. So this equation tells us that once our Fermi energy is close to our conduction band, that suggests our semiconductor materials become as an N-type. So this is a very important suggestion, because later on we will use the Fermi energy, which is either close to the conduction band or close to the valence band, to determine this material whether it's an N-type or P-type or not. So, as a sum, if we try to calculate the thermal equilibrium hole concentration here, we just use this one and do the very similar things like we have mentioned in the last slide as well. But this one also gives us estimation that our hole concentration is highly depends our energy level as well. And as we already say, we try to put the constant as a NC and NV. So NC is a 1 for the electron and NV is a 1 for the holes here. So then the different material, we can have the different NC and NV. And now later on, we will mainly consider this is as a fixed constant number that's mainly related to the material properties. So that's an example that how we start to derive the carrier concentration. From the first one, we consider the allowed energy state, allowed quantum state. That's why we have a GC and GV. And then later we apply the Fermi-Dirac distribution and then try to integrate the both. And then in the end, we can get the concentration for the electron and holes. And then in next part, we will consider a very interesting case that's what we call the intrinsic carrier semiconductor. So in the case of the intrinsic, that means that this is a material that has exactly concentration for the electron and holes. So that would be N is equal to P. So this suggests that this is a material that both has the same electron and hole concentration. And in this case, we call this as an intrinsic semiconductor. And the Fermi energy for the intrinsic semiconductor is called as an intrinsic Fermi energy. And in this case, our Fermi energy EF can be referred to as EFI. As we consider the intrinsic Fermi energy here. So now, again, we have already had an equation to describe the thermal equilibrium electron concentration. Now we will also be curious about how do we estimate the electron concentration in the case of an intrinsic semiconductor. So, but the concept, the calculation is very simple. Actually, in this case, our N0 is equal to our intrinsic concentration, which is equal to NC exponential So now, as previously, we have a EC minus EF, but now just EF is equal to EFI. So now we have a EC minus EFI. So that's our equation to estimate the intrinsic concentration for the electrons. And as the same, our P0 is equal to Pi. And now also, because now we consider the intrinsic semiconductor, and then the Pi is equal to Ni. So now Pi is equal to Ni, but again, we already have the equation to describe the P0. So that would be PV, that would be NV exponential KT minus EC. Oh no, sorry, this should be the EFI minus EV. So this is an equation that we can estimate the whole intrinsic hole concentration. Now we just replace the EF as the EFI here. So far I think it's just the different term try to replace the term replaced by the EFI so far. But we consider this equation. Now we can try to have further estimation that if we consider our Ni square is equal to the Ni square is actually can be considered this one times this one, and this one is equal to this, and this one is equal to this, and therefore the Ni square is equal to NCNV exponential. And then the top one is EC minus EV. And this is because we have the same EFI here. And once this times this is equal to this times this exponential, and this will be removed. And in the end, equation will become like this one, which now is related to the Ni square is equal to the NCNV exponential minus EC minus EV over KT. But also, we all know in the case of the semiconductor, consider the Venn diagram here. If we have the EC and EV, and now the EC minus EV is exactly equal to band gap, that's the EG. So this equation can be rewrite as a NC NV exponential EG over KT. So now we can understand the intrinsic carrier concentration is highly depends on our band gap and also our temperature. So the intrinsic carrier concentration is a very strong function of the temperature and band gap. And this concept, later we will use this concept to understand that why like a certain material that has a very large different band gap, but probably has a different intrinsic carrier concentration that can help us for the certain applications. So now what you need to know is that in the end we found out that the intrinsic carrier concentration is highly depends on our band gap, and that means that the different material that has a different band gap in the end will has a different intrinsic concentration here. And there are lots of material in the with a different material you will have a different Ni here. But the most important one that you should remember is that in the case of silicon, our Ni is equal to 1.5 times 10 to 10. That's the typical value for the silicon. So the value that is larger than the silicon, or the value of the smaller than the silicon, we can consider this is a case with a very high Ni or low Ni. So we will use a silicon as a reference a material. So with this equation, the Ni square is correlated to the band gap and then the temperature. The first one is we can start to try to have more analytical estimation for the Ni versus our temperature. So basically, with a very simple calculation, now we can have Ni is equal to this one, which in the end is equal to this one. So that means the intrinsic concentration is a very strong function of the temperature. So now you can see this is a typical characteristic where we have the y-axis as our intrinsic carrier concentration, and the top x-axis is a temperature. But normally we prefer to plot as a 1 over T or 1000 over T. This is because of the, if you try to look at the equation, this is Ni versus T. So that's why it's very often to plot the temperature dependent characteristic. In here is a temperature dependent of the carrier concentration as a Ni versus 1 over T, because that's a more correlate with our equations here. But still, this won't cause too much difficult to understand, but it's just as shown in the bottom one. So this used as a 1000 over T. So in this case, that means the x-axis to the right is a low temperature, and then the x-axis to the left is a high temperature. So now we can see that if we just look at the silicon, we can find out that the low temperature has a lower intrinsic carrier concentration, and then the high temperature has a higher intrinsic carrier concentration. And on the other hand, the intrinsic carrier concentration is determined by the thermal generation of electron hole pairs across the energy. So we have the band gap here. We have the band gap here. So this actually suggests that the intrinsic carrier concentration is mainly determined by the thermal generation of electron hole pairs across the band gap. So we all know right now we have a lot of electron in the valence band, and then why we have an intrinsic carrier concentration is because of this is related to this carrier can across the band gap due to the thermal generation of electron hole pairs. And this also means that as a high temperature, this phenomenon is getting more obvious because that's why you have a higher intrinsic carrier concentration. So the higher temperature means you have your Ni is increased. And the Ni increase, that means you have the more electron and hole pairs across the band gap. So that also suggests that once we have more electron hole pairs across this band gap, that in the end is cause higher leakage current. So this, in the end, is try to suppose that why, if you try to put a piece of your semiconductor device material in the high temperature environment, why in the end you will get always a higher current, especially the higher leakage current. So now, for the very basic expectation, we can all understand that in the case of high temperature, we always get a high leakage current. If you now already have a certain experience in your try to fabricate or characterize your device, then you will always see, like at a high temperature environment, you always have the higher current go through this. But now with this understanding, finally we have some more theoreticals to understand, to prove that why in the high temperature environment you always get a high leakage current. But on the other hand, if you try to put your semiconductor material in the extremely low environment, you always have a very low leakage current. This also is highly correlate this understanding with the intrinsic semiconductor, intrinsic carrier concentration as well. So in the end, the purpose for this equation is, as I say, the purpose to try to derive this equation is not going to confuse us. It's actually try to support our observation, try to support our understanding. Because if you are already a bit in the semiconductor area, you definitely will have a chance to really see that the leakage current, our leakage current has a highly dependent on our temperature. And normally it's a high temperature, high leakage current, low temperature, low leakage current. But now we can also use the concept of the intrinsic concentration to understand that why in the end the semiconductor material always exhibits as a temperature dependent of the leakage current. Especially this leakage current is crucial not for the static semiconductor performance, but also with the reliability, because in the case of reliability, everything is related to the leakage current. So that's a main implication that why we spend the effort to derive this equation, because in the end we hope use this equation to understand some of the device characteristic. But the pity part is that most of the students, especially they are pretty new in this field, they try to have this, they learn this equation in the very beginning of the semiconductor physics. But in the end, they learn the device in the very end of the classes. So sometimes they are not able to correlate with each other. So that's why that I just try to bring the conclusion as early to everyone that actually this equation just try to support our observation that our semiconductor material is highly depends on temperature for their leakage characteristic. And with this understanding from this equation and the conclusion that the leakage current is highly depends on the temperature, also we can start to come out with a certain idea that we can always start to use equation based on the material's property. In the end, try to prove that the certain material might have the certain good characteristic. So this is one of the examples that we all know. Now we all know that our intrinsic carrier concentration, Ni, is equation as shown here, NC/NV exponential Eg minus 2kT here. So in the previous slide, we showed that our Ni is highly dependent on our temperature. But on the other hand, this equation also shows that our Ni is highly dependent on our band gap. So if we can try to find the material that has a large band gap, so ideally, this can reduce the Ni as well. And if we can reduce the Ni, so ideally we can also reduce the leakage current here. So we already know that in the case of a silicon, this is a case of a silicon, we have the EC/EV, that's a 1.1 electron volt here. So if we can find the material that has a large band gap than silicon, for example, there's a very famous material that we call the silicon carbide, or there's a very famous material that we call the gallium nitride. And in case of the silicon carbide or gallium nitride, we have the band gap larger than 3 electron volt. So because of the band gap here is larger than silicon, so that's why we call this as a wide band gap material. So we call this as a wide band gap material. And also with the equation shown here, even we haven't tried to calculate the Ni by ourselves, but we can already estimate with a large band gap, ideally we will have very low intrinsic concentration. So that's why the wide band gap semiconductor material always have a low intrinsic carrier concentration. And as we already say, the implication of a low intrinsic concentration suggests that this is a material has a low bulk leakage current at a high temperature. So that means that at high temperature, this material still exhibit as a very low bulk leakage current. And this is a graph with Ni versus T at a different material. So this is a case with a silicon, which we have the band gap 1.1 electron volt. But now, if we consider the wide band gap material here, then we can see the Ni is dramatically decreased. So the lower Ni is equal to the low leakage current. But what would be the application needed if we want to have the very low leak current at a high temperature? And this will be the application that always need to operate in the high temperature environment. Let's say, for example, the spacecraft. The spacecraft is one of the most well-known examples that if you need to have a certain space explorer satellite in the space environment is a different planet. Not every planet like in the Earth has a very good temperature range, always below 50 Celsius degree. You know, for the other planet like the Venus, like the Saturn, always has a temperature in the very huge temperature range, can be up to more than 300 Celsius degree, or even for the 550 Celsius degree as shown me here. So in the case with the exploration, we need to have the semiconductor that can sustain for the high temperature. So in this case, we need to have the semiconductor has a low leak current at a high temperature. So that's why we need to start to think about the wide bandgap semiconductor. But of course, the space is still too far away from our typical life. The space is a life that probably we cannot always, even for the next 100 years, we still probably is a region that not all of our human beings can arrive or can try to explore. But in the case with our the case with our daily life nowadays, there's one particular application that we call the automotive. So automotive is everything related to our car. In the case of a car, especially the hybrid electric vehicle, in case of electric vehicle, the peak ambient temperature can be sometimes up to more than 150 Celsius degree, or even for the 100 beyond the 200 Celsius degree. So this is the application that need to sustain for high temperature, but this is application that pretty close to our life. And in this case, we also need to consider for the wide bandgap semiconductor technology here. And then in the last 5 years, now actually it's ongoing, everything's happening. Now this is a paper published in the 2002. In the case of 2002, there's already the prediction that if we go for the electric vehicle, we need to use a certain wide bandgap semiconductor that's suitable for the high temperature application. But now it's 2025. It's in the end, this prediction is true because of the one you see in the Tesla electric vehicle on the road. They already have the silicon carbide base inverter. But nowadays, not the automotive need to we not only consider automotive as the high temperature electronics. Actually, everything that can generate lots of heat, lots of energy consumption, that's always need to consider as high temperature electronics, because we want to make sure that those systems operate in the high temperature environment can be stable. So the Tesla for the electric vehicle is one of the examples that nowadays everyone is using the silicon carbide base inverter. So this also suggests that this is a literature published in 2002. So that's almost 20 years ago. So there was already the prediction in 20 years ago that the electrical vehicle need to use this very advanced wideband semiconductor. So that also suggests that the literature you will read now, don't feel like this is the literature that is useless. Actually, every literature you can read, I mean for the semiconductor field, lots of literature you can read now actually always suggests the future of our technology. And then in the end, one day, it always can become true in the one moment. So that's an example, but I just want to show you that the silicon carbide is this kind of wide band gap technology is not really like the technology that are still far away from our life. It's already the very intensive research and then application. So this is an official website in the NASA. I think everyone here knows about NASA. So definitely we already knew that NASA is really pioneer in the space exploration. So in their official website, they already say that they consider the silicon carbide as a high temperature electronics and sensor that can be used for the space application. And even you see this is a paper published in the 2017. This is paper published in the IEEE Electron Device Letters. So as you know, if you are the graduate student, you have one EDL, that's already enough to help you to being graduate with your PhD degree. So EDL is considered as the top journal in the device level research. So in the case, these authors are from NASA. None of these authors from the academic. These are the paper originally published by the NASA. So in this case, they also try to demonstrate the silicon carbide digital integrated circuit above the 800 Celsius degree. So why they have to demonstrate for the 800 Celsius degree? And for sure, this is not application on the Earth. This is application on the space. So with just a material property with a different band gap, and we all know the large band gap have a low leakage current. And with understanding of low leakage current, we can have the implication that this low leakage current can good for the temperature, very high temperature environment application. In the end, that everyone is trying to use this understanding, try to explore the new research in the new field. But this new research, new field has been already explored in the last decade, and for sure will continue in the future. But since we mentioned this paper, I think it also will be interesting to look at how the Native American people to write the paper. You know, for most of the USA university, you probably will see lots of the paper is written by the non-native. They are probably coming from Asia. They are probably coming from the India. They probably come from the Europe. So lots of the IEEE level paper, the first author probably is not the Native American. But it will be interesting to see the pure Native American, how they can try to organize and write the paper. So that's why they specifically to try to analyze this paper, because this paper can be something we learn that how the Native American people to write the paper. But the conclusion is very similar to what we have been already say that usually the first sentence for the introduction is always a very general overview of the status. So the wide bandgap semiconductor theoretically enable hundreds of degrees sales degree increase in the semiconductor integrated circuit ambient operating temperature over silicon, and therefore develop a silicon carbide and 3,5 nitride for temperature more than 500 Celsius degree have been proposed. So when we try to either to read the literature or try to write the academic paper, the first sentence for the introduction is just always a very general overview to the reader to understand what have been happened in the past decade. So in the past decade, already people knew about that in theoretical, the wide bandgap semiconductor is good for the high temperature, and several literature already demonstrate for more than 500 Celsius degree. And also, once we finish the general overview, we will start to mention a little bit of recent progress, because we want to highlight that there's something ongoing happen in recently. That's why we have to still keep working on this field. So the key term of the recently is also very important. That implies that we are going to say something very happened in the recent one. So recently there is a 4H silicon carbide, still a silicon carbide, like what we call the JFET here, with two-level interconnect and blah blah, has been demonstrated at a temperature up to 500 Celsius degree, which can be considered as a significant step toward the new application. For example, the jet engine inside the airplane, or the ground test, or for example the Venus service exploration. So that's the exploration in another planet in the space here. So that's also the second one. It's just also some of the review just happened in the last more recently to showcase that it's a very old research that everyone knows, but also recently we still have some of the new literature focus on this field. And therefore, but now once we finish the review, the next one is that we need to have to talk about the several issues that the already report literature haven't been addressed yet. So usually we will consider to list the issue 1. In this case, it's issue 1 and then the issue 2. But the issue 1 is more general issue. The issue 1 is mentioned the ability to operational stress semiconductor at high temperature higher than the application has proven crucial to reliability assessment and qualification. So that's a general issue. But more specifically, expansion of IC operating temperature can be expected to the new application, but not happen in the right now. So that's a second most specific issues here. So therefore, in the last one, he also put this one, say that what they have been done in the previously. They have been done in the previously for the silicon carbide JFET up to 727 Celsius degree. So that's the literature, what they have been approached. But now the last one is the main purpose for this literature. In this paper, they report the test of the silicon carbide JFET up to the 961 Celsius degree. So now if you look at this literature, and then if you don't have time to read all the detail, so now you can understand actually what they say everything. it's just probably like a 20 to 30 lines here, but the most important is always the last one. The purpose is the main motivation is the last one. So if you don't have time, just read the last one is enough, because the last one sentence is already can help you to understand this literature is something that you need to read it or not. But the rest of the just some of the general overview of the past happened, and then some of the general issues. So this is a very simple, straightforward style to write the academic paper, but it's very useful. Now you can see even for the very Native Americans, you know, it's not easy to work as a NASA. Not like, of course, you need to be very professional, but they also will do a lot of security check. They will check your background to make sure that you are very safe for them. And most important, NASA also only allow the USA citizen. So if you are not a USA, you don't have a USA nationality, they will never allow you to walk inside. So you can see these are the example that the literature written by the very Native American. Okay, so now we will take the 10 minutes break, and then we'll come back later to start to consider more calculation for some of the key number that we are interested in.
下线的事情，他说你要教那个智慧裁决。
昨天那个玉姐有那个叫我教啊，可是每个人还要再教吗？
应该是一样的，应该是您交一份就好。
对。
但是因为我刚刚按申请，它还是显示你没有交，所以。
等一下，
好。
我把那个昨天寄给那个玉姐的，你们再把它交出去。
应该是您寄到 TSI 那边就可以了。
我昨天是叫玉姐，我签好之后，我叫玉姐直接帮我寄，然后说她帮我寄了，对，不然你们就集体寄一份，但他没有 CC 给我。现在有谁不行？
我不确定，因为刚进家也是跟我说玉姐好像跟你说。
对啊，所以我要寄吗？是我要寄给他们吗？
但这个意思看起来好像是要的东西。
我们这个下线还有谁？还有那个
我跟静家的
品轩嘛。而且你先帮我记一下，我填到中午之后再记。我先把它发出去给你们。
我觉得应该是我。他都没讲，绝对不用讲。他之前电子
好，我更新给你们。好。
是这个，他说这个往正 X 方向是前面这个位置，为什么会这样子？就是他说 traveling wave 的正 X 方向是 the first term，
对，
这个，
对，对他这边的话，他这边是他这个表示是用这个
机会，
对，他这个的话，他这个表示因为这是驻波里面，所以他这边的话，这个是正 X， 这个是负 X， 你可以看一下那个本身这个 exponential， 用那个 exponential 表示正负方向。
它的图形，
什么意思？
就是为什么这个会导成正 x 方向的意义？就是它这条方程式为什么会是？
你可能要看一下工程数学。工程数学这边有教，就是为什么 exponential 的方向正的话是往正的，exponential 方向负是往正，它就是一种把它拆成一个，或就是一个就正跟负，只有两个方向，它就用两个一旁的 exponential 去表示。对，主要是这样。对。
那个 B T，
对。
我之前的 C 大长这样，
对。
然后因为它都会续成
对。对。
所以我后来改了 C 大，
对，
就是我在里面
加10秒的 recovery， 对。
那杨毅是说就是他们每个人 BTI 是不会加这个 recover time 的，所以他请我再跟他确认一下是有没有。
可是你 fresh 加这 recovery 之后，有加入 recovery 跟没有加入 recovery 会有这个明显的差别吗？
就是我礼拜6的时候量测的时候做，然后是
正常来说加会比较好，加是可以去避免说你这个 fresh 的 characterization， 如果假设它有影响的话，对。可是你的
就是之前做出来的结果就是很不一致。
对，所以你会有加 fresh 不是有加那 recovery 比较好。对。
可是然后杨毅那天有提醒我说，就是iMac那边有希望我把那个 VG 的 bias range 改小一点。
哦，也可以啊，你可以把它改小一点，对。
负6到0。
对，可以啊。
但是我负6到0。
负6，其实重点是负6到。
就是0.5。
你可以负6到负
6到负。
一定不要超过0，对，然后让它 VG 越负越好。然后你之后你现在可能比较有一点经验，我觉得你可以创一个叫做 ENS， 我看一下，你可能看一下我的 paper， 就专门在讲测 BTI 的，杨毅他们还没测过，但其他人有测过，看一下，这个，你看到这个是讲 BTI 的，对，他现在的话就会用这个所谓 ENSN 的方法。ESN 基本上它就只量1点而已，所以它就不用扫整个 flow curve 去，它只量1点。所以它的 idea 就是说，我是会先量一条这个
一条完整的 IV curve，
然后我接下来只量这一点。所以接下来你有 shift 的话，我就只给一个 VG， 然后你就会看到一个 ID 嘛。所以假设你觉得有会有 shift 的话，变这样子的话，所以你量 VG 的时候，你就会看到你的 ID 会下降。
对。
但是你可以借由IG 的下量去直接推估它 VG shift， 因为它就是这样 shift， 这样 shift 这样，这是你的 VG shift， 会导致你的 ID 下降。对。所以你可以根据你的 ID 下降量去推估。
所以它应该算是用 ID 需求量去回推说它的 VG。
对。然后这样的话，你只要量1点而已，所以你这样每次都只要量1个点。那你每量1点的话，就可以减少很多 fresh characterization。
因为我看梦者之前用那个 WGFMU 量的话，它的 bias range 很小，大概0.6以内而已。
你可以先用它的，那之后的话就要用到这种。对，它就是一个 Vmax， 对 ，paper 是这样的。这个在 iMac 现在蛮常在使用的，对，但是我觉得他们 iPhone 还没有用到这个，所以也是我们之后可以把它使用的。
好，没有，因为杨毅突然跟我讲这个，我就有点害怕，说我谁有没有错
？10秒可以啊，10秒 recover， 你是 fresh 10秒 recover， 可是你最后 stress， 不过你最后 stress 完的 IDVG 也是要让它的 bias 越来越小。因为对，其实我比较不 care 的是 fresh 之后的，就是你回到你的procedure。对，你这个的 characterization 是还好，但是比较 care 的是这个，因为你每次过来之后你会这2个 IDVG， 所以你要避免这个 IDVG 会不会影响到你的 stress。
没有，我每次量 IDVG 后面都会再加一个 recover。
那这样就不行啊。对啊，我以为是你只有前面而已。可是你这 stress 完就 recover 的话，那你 recover 时间就大于 stress。
是就是 fresh， 然后
recovery，
然后
stress 0秒0.1秒，然后可这中间是没有 recovery 的。
没有。
对啊，这中间是没有 recovery 的。对啊，如果说这中间有 recovery， 那就不行，因为这样的话，你的 stress 10秒，但你 recover 10秒，那你就没有量到。对啊。
那我是 我是 stress 完，然后马上量 IDBG。
对。
那这个 after stress 的 IDBG 结束之后，我会 recover，然后再让它接着 stress。
哦，不行，除非你是换元件，除非你这个元件完了之后再量下一颗，在同这个元件上面你可能要这样量，但是基本上你只有这边可以有，
就只有前面这一段。
对，但是后面，但是如果你同时把它的任值都调小，你顺便可以去掉这个，这我不确定。但是这中间的这个你的 IDBG 一定要是对很小，对，然后这中间是不能有趴的。
那我再改一下，等一下。
我们现在那个文茂现在那边怎么样？
我妈那边后来说要给我们写元件就没有下。
还没有下文，但是我们还要用旧的元件 demo。
对，然后我们那天用了那个就是等一下，就是加它的by，
对，
就是在那个 stress 点，就是应该是 BTH-3，然后40跟那个0。
OK。
然后我们有发现，就是它的趋势没有像陈他们做的变形。它应该正常来说，它的图应该是要长这样子的，可是我们图会变成这样子。
可能说明是不同的机制。而且我们下礼拜讨论一下。但我想说，就是那部分的话，可能还是要麻烦你，就是带着这个一档。对，
有，我们通常都是礼拜一晚上练。
好。你看一下这个，因为之后我们等它阴墨元件来的话，我们就要阴墨元件就更敏感，因为其实你现在是-5扫到0，所以你知道大于0或者1，但现在没有大于0，所以我觉得这个现在可以，但是我们当然可以现在多做一点理解。等到阴墨元件的话，你这就会3、5、4，所以你这所有的 IB 使用就会产生力。对。
可是老师，我那天礼拜六自己做的时候，我就没有加那个 recovery time，然后我发现我一开始然后加到中午之后，然后0.1秒在这里，但它慢慢一直有不足。
那也不错啊，那可以慢慢。你说是慢慢一种是说在 IB sweep。
对，就是它 stress 完之后，它就是最开始其实
在 stress 为什么做？
就是 after stress IDBG。
那几幅 stress？
6幅跟9幅都发现。
正6正9。是有些朋友在探讨，在 positive stress 的时候，它会有 negative shift。是有一些，不然你可以看下这边。
有，我这礼拜3，我上礼拜跟老师讲的那个ABTI。
anonymous 那个嘛，对。然后有一篇，我记得那个有一篇那个，你可以看一下。
不然你可以看看这个，你看看这2篇，然后这一篇，
看看这2篇，他们是 MIT 的，他们有做过，但是我不确定他们结果怎么样。但是也在 study BTI。对，这一篇跟这篇。
那我再看一下好了。
对，好，
谢谢老师。
OK， 好。你有记吗？你今天是什么？我没有抓紧你。
没有到。我看一下。这个是OK， 好。
Okay, so let's continue. So let's try to get some more like equations here. So as we already mentioned the concept for the intrinsic semiconductor, we also mentioned the concept of the intrinsic Fermi level. So we will be interested to look at what would be actually the position for the intrinsic Fermi level. So the intrinsic semiconductor consider the case of the electron hole concentration are equal. So that means our previous equation NC exponential EC minus EFI over KT is equal to NV exponential the EFI minus EV over kT, because now the electron concentrations are equal to the hole concentration. And based on this equation, we can try to solve the EFI as shown here. And therefore, the EFI is equal to this one plus this, or this one plus this one. So the difference between the EFI and the middle gap, so we can also define the mid gap here. So the mid gap is exactly in the middle. So we define the EC plus EV over 2, which is a mid gap here. So now we can understand actually the intrinsic Fermi energy is not exactly in the middle gap. There's a slightly difference. Although we consider this is the electron and hole concentration are equal, but actually if you try to estimate the EFI, which is not exactly in the middle between the EC and EV, and this is because of that the electron and hole has a different effective mass, so that will cause a very minor difference between the EFI and the E middle gap. Okay, so since we finished the discussion of the intrinsic, therefore we will be interested to look at the case that we can add additional species inside. So the intrinsic semiconductor might be an interesting material, but the real power of a semiconductor is realized by adding small control amount of a specific dopants or impurity of the atom. So we can add intentionally additional dopants inside, and that can actually create something different for our semiconductor material. And the material that we have the dope semiconductor is that we call as an extrinsic material. So if you look at the crystal, the latest arrangement here, this is intrinsic material that everything is with only considered as a silicon. But in the case of the extrinsic, that means we have a silicon here. We all know the silicon have the four so that's a typical one. For silicon, we have the we have a certain like formation of the covalent bond with the nearby of the silicon atoms. But if we replace a one, if we replace a one as a different atom, for example, we dope the arsenic here. So arsenic has a 5 electron in the outer shell, which will be the 4 is being bonded with the silicon, but there will be the additional 1, which is free electrons can be flow to the anywhere. So then in this case, since if you look at the latest arrangement here is not the pure silicon anymore. We have the additional arsenic being doped here. So in this case, we call this as a extrinsic semiconductor. So now consider we add a group 5 elements such as a phosphorus, but in this case we use the arsenic. And then the group 5 element has a 5 valence electrons. And 4 of these will contribute to a covalent bond with silicon atom. But there's a 1 will be there's a 1 atom that not being bonding with the other 1 here. And because of these additional electrons here, so in this case, we can consider the electron concentration is higher than the intrinsic concentration. And in this case, we consider this as an N-type. So this is something that we already mentioned in the several classes before, that we consider that we try to dope our material and then we can change the material property from the intrinsic to the N-type or P-type. But now also the similar things is that we can also not only for the no matter for the donor acceptor, we can actually have the extrinsic materials, and this extrinsic material will have the case that the full of the electrons, which will be the N-type, or full of the holes, which will be the P-type. So in this case, you can see the left-hand side is 1 that we dope with arsenic. And in the case with arsenic, we have a 1, 2, 3, 4, but additional 5 here. So this is N-type because of arsenic actually donate 1 additional electron. So that's why we call as a donor here. But on the other hand, similar, we consider the silicon here. But now if we try to dope as a boron, so in the case of boron, only 3 electrons in the outer shell, which will be bonding with the silicon. But now we have the empty space here. This empty space allows electrons flow here. But also that suggests that this is a empty, that we call the holes, which will be the opposite behavior compared to electron. So in this case, we consider as the holes here. And why? Because of this empty place can accept 1 electrons. So that's why we call this as an acceptor. So in this case, which is a P-type. Because of now we have the additional hole, and then that can have the 1 electron flow in, and then that will become the P-type here. So this is a case for the P-type as well. So that's why we use the donors of an acceptor as a term here. So try to understand the concept of donor acceptor from here, because in here we still in the very basic case to discuss of the donor and or acceptor, because in later on in the future, once you are trying to take care of some of the trapping issues. So you will face a lot of the turn is also related to the donor or acceptor here as well. But in that case, will be much more complicated, but the definition is the same, like shown me here. So now we all know that in the end, we definitely will not use intrinsic, because we actually will like to use extrinsic semiconductor, because we can dope some certain atom. And once we dope the atoms, we can change the material property for our certain purpose. But we will not always draw in this way to understand this behavior, because this is a schematic and then this is very complicated. We want to use the same concept like the Venn diagram with a certain energy level to describe this behavior. So, if we first to consider donor impurity atoms, so the donor electrons can be elevated into the conduction band and leaving behind the positive charge phosphorus ions. This text is very difficult to understand, but if you look at the figure, which will be much more easily to understand. So what this sentence want to say is that right now we have the donor impurity here, but also remember that once we put a donor, we have to consider the energy level of the donor. So we can reconsider the behavior of the donor atom as a donor energy level inside the Venn diagram, which is here. So now we dope something, and then this dope something in our understanding of the quantum series, everything, trying to consider the semiconductor in the quantum mechanics, in the end will all become the discrete energy level. So therefore, we put this discrete energy level to describe these donor impurity atoms here. So, but in the end, these donor impurity atoms can actually start to contribute the current. And how this contribute? This is by considering we have the conduction band, we have the valence band, and we have the donor energy level, ED here. And we all know that in this case, that the original, the donor energy, it means that this is the case we consider the group phi. So that means the group phi is one that carry a lot of additional electron, and this group phi atom can contribute lots of free electron. And this contribution of a free electron in terms of energy level is actually as the electrons will be jumped to the conduction band, because we all know the conduction band is empty. So now the ED is a donor atom that has a lot of free electrons. This free electron will jump to the conduction band, and this jump to the conduction band in the end become the current. So this is how we describe the current flow by using the Venn diagram theory, which consider the additional donor atoms here. So this is something that we try to transform the concept from the 2D lattice arrangement to the Venn diagram with the energy level ED consideration here. And these donor electrons can be elevated to the conduction band. So this sentence try to describe here. This donor electron will be elevated to the conduction band. And once these electrons being elevated in the conduction band, and that will left a positive charge behind. So in this case, we will have the positive charge here. So this is how this sentence try to describe. So the sentence want to describe is that you have the donor energy, and then you have this donor energy, the donor electron will be jumped to the conduction band, and once you jump to conduction band, you will left some of the positive charge behind here. So the electron in the conduction band can now move through the crystal, generating a current. But the positive charge ions will be fixed in the crystal. So that means that this will be contributing as a current, but this will be fixed in the crystal here. And this will result in material as an N-type semiconductor. So that's because we have more electrons than the hole in this case. So we consider this is an N-type semiconductor. And as you see, the critical action here is that the electron need to be jumped from the donor energy level to the conduction band. So therefore, the energy difference between here is crucial. If the EC minus ED is larger, if you have an ED here, and for sure that you will be very difficult, the electron can jump to the conduction band. But your EC minus ED is small, then these actions will likely happen, will be easily happen because of your EC minus ED is small here. So this number is what we call as ionization energy. The approximate energy required to elevate the donor electron in the conduction band, this energy is referred to the ionization energy. Ionization energy. Ionize is not the term like we typical to learn from in the past, and also if you try to translate in the Mandarin, also still very difficult to understand. What does mean the ionized energy? Just try to remember this term as English, because if you try to translate in the Mandarin, it actually doesn't help. So in any way, this just the energy that can require from the donor state to the conduction band. That's what we call the ionization energy here. So with the understanding of the band gap and then the energy level. So if the ionization energy becomes small. So that means that the electron in the conduction band is increased. Right? Because of as I say, if this gap is getting small, for sure, more of electrons are easily jump to the conduction band and contribute as a current here. Normally, in the case of silicon, we almost neglect the impact of ionization energy because ionization energy is very small in the silicon. That's why that in most of the semiconductor, because in most of the semiconductor physics and device, this kind of lecture we mainly talk about the silicon. We won't talk about in the other material. But now, if you try to work on the additional material, other very fancy small band gap, wide band gap, 2D or whatever material, the ionization energies become very critical because in other semiconductor material, ionization energy is always large. So always large, it means that you can expect that whatever you try to dope in semiconductor, we cannot guarantee like 100% to contribute as an electron, as a current, because of the ionization energy is large in the most of the semiconductor material except for silicon. So that means this actually the concept be very crucial for the most of you, because I think in this class where most of you is not purely working on silicon, it's always working on the something very advanced device, advanced material. Okay, so similarly, we can also define the acceptor energy state as shown me here. So in this case, we have the ECEV here, and we have the acceptor state here. EA here. And then in the case of the acceptor state, these electron position can be solved of the holes in the semiconductor material. And the hole can move through the crystal and generating the current. So you will have the holes will be jumped to the valence band. And similarly, once a hole jump to the valence band, and then we will have these holes will contribute as a current. This will be the contribute as a whole current. So then we will still have the negative charge will be left behind and fixed in the crystal. So show me here. So therefore we can refer to this as a p-type material. And then as the same, the difference between the EA and the valence band is that we call as ionization energy. Okay, so let's look at some of the ionization energy in the silicon with the different impurities here. So in general, you can figure out that this impurity, no matter for the donor or the acceptor, their ionization energy are very small. It's in the value around 0.045 or 0.06. So in this case, we actually have the very small ionization energy. The very small ionization energy suggests that the valence band and then the conduction band, and then we, in the case with silicon, we have the EA here, and because of this EA is very small, that means this is 0.045 electron here. For example, if you consider as a boron here, but this EA, since this ionization is very small, that means if we try to dope the boron of the 10 to 20 of their concentration, then we can make sure that in the end this boron can contribute as a whole very close to the 10 to 20. So that means we dope the boron in the concentration of the 10 to 20, and then in the end we measure the whole concentration will be very similar as a 10 to 20. So that means the small ionization energy suggests that we almost got more than 99% of ionized. So this means that whatever you dope, because you have to first to understand that you try to dope the boron, you try to dope the phosphorus, you dope the arsenic, they will, in the beginning, they are not electron, but they will become the electron once this electron jump to the conduction band. So the doping concentration is not equal to the carrier concentration. Your doping of arsenic is not equal to electron concentration because you have to take into account of this ionization energy. But luckily in the silicon, because the ionization energy is very small, so your doping concentration can be very identical to your electron and hole concentration. This is because we have very small ionization energy. But that's why in the silicon, even most of the lecture in the semiconductor physics device, we just quickly go through this concept and we won't bring too much attention because in silicon, the doping of the boron will be almost identical to the whole concentration. But we are not only working on the silicon, we are working on the all very fancy exotic semiconductor material. But for the other case of semiconductor material, this ionization energy becomes very crucial for consideration. Like, for example, in the case of the one that I'm very familiar with, gallium nitride. In the case of gallium nitride, we still have the same EC and EV. But now if we want to make the gallium nitride as a P-type material, which is not easy that we can expect like in the silicon. Still the same, we can dope several atoms. But the problem is that these dope atoms actually has an energy level which is far away from our valence band. Probably can have the ionization energy larger than 0.3 electron volt. But 0.3 electron volt, sometimes difficult to understand that how do we judge this value is big or not, but it's always the most useful ways to compare with silicon. In the case of silicon, it's only 0.045. But now if we use another material that has 0.3, so which is almost 10 times larger than the case of silicon, right? So our ionization energy in the gallium nitride is 10 times larger than silicon. This also suggests that the carrier here can jump to the valence band. The probability is highly decreased because now you get a larger distance. For sure, the carriers are not easily to jump and cross to the valence band. And in this case, we get less 10% ionized. So what does it mean that less than 10% ionized? That means in the case of a gallium nitride, we normally dope the magnesium, this kind of material, as a acceptor. So we try to use the magnesium to transform the gallium nitride as a p-type of gallium nitride. But now we will find out that if we dope the 10 to 19 of a magnesium, in the end, you only have less than 10% being ionized. So that means you can always get only 10 to 18, smaller than 10 to 18 for the whole concentration. So this becomes a problem. This becomes that we cannot create a very good p-type material for gallium nitride because in the end, the whole concentration for p-type in the GaN is always smaller because of we always get sometimes 10%. In the very poor technology, sometimes 1%. 1% means that you have a put layer for the 100 magnesium, but only one of these 100 will become the host. So the percentage is very, very small. And this challenge is actually becomes a very crucial challenge for the gallium nitride. And then the people who solve this challenge, in the end, they get the Nobel Awards. This is from the Japan professor. Because they find a way to try to transform the gallium nitride as a p-type gallium nitride. And that's with this p-type gallium nitride, finally we have the gallium nitride LED. So because we need to have a LED, we need to have the LED is just a basic idea with some of the P and N diode. So we need to form the p-type gallium nitride. And then if we have a good p-type gallium nitride, we can have the good LED. And the professor from Japan, they find a way to increase this ionization energy in 20 years ago. And this innovation, in the end, creates a whole new device called the gallium nitride LED. And then, of course, the LED now is a technology that we cannot live without LED. All of the light becomes LED nowadays. So because of his solve this issue, try to increase the p-type concentration in the GaN. In the end, he gets the Nobel Prize award. So you can see that in the end, the understanding this knowledge is very useful because of just the knowledge with ionization energy. Most of us will get ignored because in silicon we don't face the issue, but in the other material we face a lot of issue. In the nowadays, we still face a similar issue in the other materials that always has a large ionization energy. Okay, so as I say that finally we understand the how to use the energy level to describe the extrinsic semiconductor, we also understand there is a Fermi energy level. But we can also use the similar drawing like we had before to understand, to calculate the electron and hole concentration here. So the similar plot has been drawing again. I believe everyone, even just cannot catch up 100%, but you must already very familiar with this plot because it's showing again. So again, we will use a Venn diagram. So as I say, we are the engineers, so we try to make things simple. Although in theoretical, it's very difficult to understand. In terms of equation, sometimes also very complicated. But with a simple drawing and schematic, that's highly help us to understand the meaning behind. So we use a conduction band here. This is a graph that we have, the plot that we have been shown. But now we consider what if our Fermi energy is not in the middle. The previous plot, what we draw is the EF is in the middle between the EC and EV. But if we consider the EF is here, so what will be the change for this plot if we have the EF close to the EC? So similarly, let's do the step by step. We have the, once we consider EF close to EC, we can still draw the GC and GV, but in here they call the DC and DV, but it's the same things. This is DC. It's the same one that we call as GC before. And also in the bottom, we have the DV here. But now the only thing changed is now our EF is close to the top. So this also will change our distribution. Our Fermi-Dirac distribution will be changed. So that means our distribution will shift completely to the upper, which will become like it in this way. So this is our FE here. So in the past, we have in the middle, so your curve is like in this way. Sorry, I should draw more precisely. So we have this something like this one. But now, so our Fermi Dirac distribution is shift towards the top. So that means the overlap region of this is become larger. The overlap region become larger suggests that the electron concentration here is increased because of the areas become larger, so the concentration is increased. Also, this becomes smaller because of the area is become smaller, and this is also another way to understand the impact of EF on the concentration. So because now we can understand the electrons concentration is larger than the whole concentration, which this is an N-type material. And the conclusion are the same, like the one we say that if you look at the previous derived analytical equation that the EC minus EF becomes smaller or N0 is increased. This is the same, very consistent with this graph that our EC minus EF is smaller. That means your EF shift towards up. And then once your EF shift towards up, then your overlap area is increased. Then in the end, your concentration is increased as well. So everything is very consistent. Just depends on which angle you try to understand. Of course, some of the angles are relatively complicated if you just try to look at from the theoretical equation. But I believe in this drawing, you get a much more good sense that how the EF will influence our electron and hole concentration. So a nice drawing is shown in the next one. So if I don't draw very good, this one is showing the better, that exactly the same. So this is in the thermal equilibrium. But now if we shift the EF toward the EC, you actually start to see the area is increased. So the area increase suggests that we can get a higher electron concentration, but also the whole concentration is decreased as well. So if you just don't remember the equation, and then every time you feel very complicated to draw this complete figure, because the figure drawing takes some time. In the end, the conclusion is just if our EC minus EF smaller, our N0 is increased. So that's the conclusion. So now we don't have to every time to do this step by step. We can purely consider the position of our EF close to the conduction band or valence band. Then we can already know that this is N-type or P-type material. If we don't remember this equation, that's still fine. We can use the Fermi energy level as an indicator for us. So similarly, if EF minus EV becomes smaller, that also suggests our P0 is increased. And in the end, this will become as a P-type material. So the purpose we spend so much time to derive equation is not like we have to every time to use the equation. We not have to every time to remember this equation. In the end, is this equation just try to support our understanding with using the band diagram. That's enough to explain, to understand, and then we have the equation to support for our observation and understanding. Okay, so we can still try to have some equation here. So we already know the N0 is equal to NC exponential so we can start to play a little bit trick here. We consider the EC minus EFI plus the EF minus EFI here. And with considering this equation, then we can further derive here as minus EC minus EFI over KT times exponential EF minus EFI over KT, and then we can consider this one as a intrinsic carrier concentration, because now we calculate the EC minus EFI, so now we can call this as NI, which is intrinsic carrier concentration, which is EC minus EFI here. So, to further have some more interesting law here, we do the certain additional calculation. This calculation is not that difficult, just you need to have some patience to go through it. So as we already have, the N0 is equal to Ni exponential EF minus EFI over KT, and the P0 is equal to Pi exponential KT EF minus EFI. So now we can try to times the N0 with the P0. So the product of the N0 P0 becomes NC NV exponential minus EG over 2KT. So that's also equal to the Ni squared. Therefore, we can have the law that we call the mass action law is equal to here. So in here, we just try to have another law, try to derive another law as shown in here. Let's just go through the text here. An intrinsic semiconductor in thermal equilibrium does not contain an intrinsic semiconductor concentration, although some thermally generated carriers are present. The intrinsic electron hole carrier concentration are modified by the donor or acceptor impurity. Therefore, we might think of the intrinsic concentration Ni simply as a parameter of a semiconductor material. So in the end, the conclusion is that how do we try to how do we try to judge the one material? So we can use Ni as a parameter to evaluate the one semiconductor material. So I think that's a purpose in the end. So the Ni will become the parameter of the one semiconductor material. So in the previous case, what we mainly talk about is always your EF is below your conduction band. But in reality, it is also possible that your EF is above your conduction band. So everything is possible, especially the EF can be also above in the semiconduction band. So in this case, the band diagram will be drawn as here we have EC, we have EV, but now our Fermi energy is above the EC here. So that's the case when the concentration of electron in the conduction band exceeds the density state of NC. So this is the case here. So we have the EF, which is above the EC. And in this case, we call the degenerative dope N-type semiconductor. And also similarly, we can have the EC, EV here. We can also have the case that our EF below the valence band. Also, this is a case when the concentration of hole exceeds the density state of the NV. And in this case, we call the degenerate P-type semiconductor. So, from the meaning, the name of this kind of semiconductor degenerate, it's relatively difficult to think because of this is even you try to translate in the Mandarin, it won't help. But you can consider that in this case, you actually transform the semiconductor toward a metal. So if you look at the Venn diagram for metal, that would be very similar to this case. So this is a case that you have extremely high doping. So that's why your Fermi energy will be above your conduction band. Because most of the case, if our doping concentration is not that high enough, the EF is always here. But once you have EF above your EC, that means this is a very high concentration case. And in this case, that's what we call the degenerate semiconductor. This is not a typical semiconductor. This is another type of the semiconductor case. So this is what we call the degenerate semiconductor. Okay, so the next one is that we were interested to the case that, as we already said, that we can consider the ED, which will be the donor energy level. And then we have the ND is a concentration of the donor atoms. So if let's try to put some number here to get some sense. If we have the 10 electrons here, and then in the bottom graph is we consider that once the ND is ionized, so once we have the ND is ionized, that means that there will be a certain of the electrons will be jumped to the conduction band. For example, in this case, we have a 9 electrons. But still, we total have a 10 in the donor state, in the donor energy level. We have a 9 jump to the top. That means we have a 1 left. So right now we have a 1 left, but also as previously said, we have a 9 electron jump to the top, so that will create a 9 positive charge left behind. So this is a 9 positive charges. Will be left behind. And now we can consider that the several different names for these different the carrier in a different position. So this the bottom one is we call the ND, and then the left behind positive charge is called the ND plus here. and we also have the ND here. So from this one, now you can understand that actually in the end, your total has a 10. So the total has a 10, which will be equal to this plus this. Try to not to be confused. This should not be say as this one is ionized. I will say the process is ionized, but the total ND is here. This is total ND. So that's why this equation is valid, because the total is 10, which will be equal to 9 positive charge left behind, and then 1 that's a ND in the donor state energy here. So this is how this equation is coming from. And also, once we consider the donor and acceptor, we also need to consider the statistics here. So we all know that the distribution function for the donor electron in the donor energy state is a slightly different from the Fermi-Dirac function. In here, we won't do any proof. If you are interested in, you can look at the textbook and find some of the literature related to the solid state series here. So in here, the ND is the concentration of electron in the donor energy state here. So we have the equation shown me here. And this one is something that we derive from the last slide here. And the 1/2 factor is sometimes written as a 1/G. And the G here is called the degeneracy factor here. And P A is a concentration of hole in the acceptor energy state, and have the similar equation as we show. This is a ND. This is a PA here. So with the consideration of this equation in here, we get the conclusion here. So the conclusion tells us that this is ND over ND plus N0 is highly depends on EC minus ED. And then the EC minus ED is ionization energy, right? This is something that we already defined before. This is the gap between the conduction band and then the donor state energy. That's the EC minus ED here. So with considering this equation here, as I said, the derive of this equation is at least not that very important in this class. It's because in here we mainly try to understand the physics behind. But if you are interested in, for sure you are welcome to check the details later. And the most important is try to use this equation to understand the status of the ionization. So this is a question. In the end, determine the fraction of the total electrons still in the donor state. So that means this is a question curious that once this donor state is being ionized, still how many electrons still left in this position. So consider the phosphorus doping with some condition, and therefore we put this one inside. In the end, we can understand the result is only 0.41%. So 0.41% suggests that with such small ionization energy, only 0.4% electron in the donor state. And then more than 99% above the conduction band. So in this case, this example shows that very few electrons in the donor state compared with the conduction band. And this is a case that we generally call as a complete ionization. So essentially, all of the electrons for the donor state are in the conduction band, since only 0.4% of the donor state contain electron, and the donor state can be considered as a complete ionization. So this is the same phenomenon that we described before, that the ionization energy in the end can influence how much of the electron holes can be generate, how much the electron holes can be ionized. So this is exactly the one I mentioned here. This one, as I already said, once we have very close the EV minus EA or the EC minus ED, once the ionization energy is small, then everything is being ionized. Less than 1% is stay here. But when we talk about this line, we don't have any formula. This is just a pure speculation from this graph from here. This is just a speculation that based on what we understood from the band diagram. And as I already said, once the ionization energy is larger, then we will have this very small percentage being here and most of in this region. So this concept, this observation is being proved here using this equation. With this equation, so we can confirm that with a small ionization energy, 0.045, then you have a less than 1% stay in the donor state energy, but the more than 99% is being ionized, and then contribute as electrons in the as a current in the end. So this is case we call the complete ionization. And if you are interested in, you can try to replace this number with minus 0.3 electron volt. Then you will start to see how huge difference can be, because of you change from this is exponential minus. You change from minus 0.045 to minus 0.3. Then you can surprise to see that the huge increase of the carriers cannot be ionized and stay in the donor state. So that's the point from this slide. Okay, so I think we will stop here because I think it's quite a huge amount of the new things for everyone, and I believe you need time to digest. So we'll stop here, and then we will see each other again in next week. Thank you.